values. And we can actually see this as follows. So this is a little picture that we might paint of a computer's memory. So if you think about now your own computer, you've got like a gigabyte of RAM, 2 gigabytes, 4 gigabytes, something like that. Let's just assume that your RAM looks like a rectangle. And RAM is, again, 1 gigabyte, 2, 4 gigabytes. And bytes is the key word there. If you have a total number of something, you can number those things. So this thing at the bottom left, this might be byte number 0. If I move my hand over a little, that's byte 1, byte 2, byte 3, byte 4. Then I go up to the next row. That's byte 5, 6, 7, and 8. In short, we could assign like 1 billion unique numbers to every little square portion of this picture, if this whole rectangle represents my computer's memory. So what happens when you actually run a program? Well, when you run a program, what function gets executed by default? It's just main. Right? So main gets executed by default. Main might have some local variables. Where do they end up? They end up at the very beginning of your computer's memory, let's say. This is a little bit of a simplification, but they'll end up at the bottom left-hand corner there, inside of the rows labeled main. Now, main can take arguments. Thus far, we've been writing int main void. So right now, there actually are no inputs to main, but we'll get there. Main's locals means all of main's local variables might end up there. But what if main calls a function like printf or getInt or, in this case, swap? Where does it end up? Well, where does swap and all of its local variables end up? One layer higher, literally in RAM. If something starts here, the next function ends up here. The next function's variables end up here and here and here and here and here. So where we say foo, and foo incidentally is like a mathematician might say XYZ, computer scientists say foo bar baz, quux, and then there's some other crazy words. Just when you need a verbal placeholder. Foo's local variables end up on top of main's. And guess what? If foo calls its own function, where does it end up? In memory here and here and here. So again, one of today's and next week's themes are security. Turns out that this is actually a brilliant way of hacking a computer. If you have the ability to call a function that calls a function, that calls a function, that calls a function, if you do this enough times, you can actually start to change the contents of a computer's memory, potentially in dangerous places. And so if you've ever heard of a word like a buffer overflow exploit, or more generally, a website being hacked, to this day, it is still incredibly common to hack into computers by passing them bigger strings or bigger numbers than they were expecting. And what happens is those strings or numbers start filling up space in your computer's RAM at the bottom left, but it gets so big that it overwrites something important. And for today's purposes, that's bad, because if you overwrite something important, you can actually trick the computer into executing almost anything you want. But it derives from this problem here. So just to hammer this home, who cares about these rectangles in this depiction of memory? Pictorially now, if you have x and y and they live inside of main, just graphically, they are not accessible to foo, and vice versa, because they're ending up in different locations in memory. So let's actually go back here and try fixing this. So I could fix this by introducing not a local variable, but a global variable. So let's scroll down here. The only thing different now in this version of swap is that I'm actually going to, sorry, not of swap, in this program, I'm going to try to solve this problem in this way. So let's scroll down here. And let's simplify this. Rather than involve two variables, x and y and swap, let's simplify. Let's instead change the story to a function called increment. And increment's purpose in life is just to increment a variable. So let me change this real fast. Let me break this, and then we'll fix this. So look at main here. I've got an int x gets 1. I then claim initialized, because I've initialized it to 1. X is now 1. Incrementing, ... I call the increment function, not even passing in a value here, incremented, and then I claim it's some new value. So if I look now at increment and I try to do this, will this work or not work? So no, and what's the short answer? I'm trying to do x++ inside of increment, but so it's a void function, which means it has no output, it doesn't return anything, but more worrisomely, what else is also buggy here? Yeah? Exactly. This x was not declared inside of increment. It was declared inside of main, which means you don't have the right to actually do ++ here, and you can't even compile this. If we run make on this, it will just yell at us that x is not initialized, because it's not in scope. So how can we fix this? Well, you know what? Rather than make x local, let me try another little trick and scroll up here. And let me actually declare my int outside of this whole program. And if I declare the int x at the very top here, now there actually aren't curly braces anymore because I'm outside the huge main file. But is x, do you think, in scope or not in scope now with regard to the rest of this file and all of its functions? So it actually is in scope. So just as before, where the quick fix was just copy and paste our whole function, put it at the very top, here too, we can kind of fix this by just putting our variables at the very top of our program. And now both main and increment and any other function here can execute them. All right, is this a good thing, bad thing? In this case, it actually solves the problem very reasonably, and it gets the job done. But what's maybe a downside of these things now called global variables? Global in the sense that they're not inside of functions, they're inside of files. Someone, how about over here? Any? All right, over here. Here we go.
So for example, if you globalize x over there and there's another function with a very long program and you accidentally use the same variable.
Good. Yeah, so if you start thinking ahead, and granted this is a little hard to do when we're just implementing pennies thus far right now, and similarly short programs, realize that this is also a solution that doesn't really scale very well. Before long, we'll be writing more sophisticated programs that have more variables than just one. And so again, as a matter of good design, if you just start plopping all of your variables at the top of your file as globals, you totally defeat the purpose of trying to declare your variables as close as possible to where you actually use them, which lends themselves to readability. And it's just easier to understand what your program's doing if you do everything really only when you want to use something. If you're just littering the top of your file with these global variables, long story short, this does not scale well. And in fact, once you start using other people's code, libraries or APIs, like I referred to a week or so ago, things like even CS50's data APIs for course catalog data and shuttle data and dining hall data and the like, once you start using code that other people have written, my God, what if you use a variable called x and that other person uses a variable called x, right? What if the person who implemented printf in a file called standardio.h and another file, standardio.c, what if he or she also decided that he or she needed a variable called x, so he or she put x at the top of their file? Now you have collisions. And this suggests that now you can't even use the variable x if you want to use printf. So again, long story short, putting stuff at the very top of your file in terms of variables tends not to be the right solution. So they exist, and we'll see cases where global variables are compelling, but thus far, this is not, in fact, the right solution. Well, let's see if we can't now completely abuse some of these ideas and see what bad things can happen. So I'm going to go ahead and save this as, let's say, bad.c. And I'm going to go ahead and zoom in here. And I'm going to do something like include, let's say, standardio.h. And I'm going to have int main void. And then here I'm going to do something. I don't know what yet. I'm going to then have a function called void bad. Can be the same thing as the file. Is it going to take any inputs? No, not even going to take any inputs. So I'll say void. But I could have it take input. And now here I'm going to say printf. Oh, you know what? I will have it take input. Let's have it take an integer n. And what I'm going to have it print out is that value of n followed by a new line character with %d. So all this function does, and it doesn't seem all that bad thus far, all it does is it prints out the value of its argument. So how do I call this? Well, let's do int n gets, let's say, 0. Let's call bad of n. And that's it. So what will this program print when I run it? So I think it will just print 0, right? Quick, super quick sanity check. So if I do make bad, oh my gosh, so many mistakes. All right, good. So when you see lots of mistakes, just listen to everyone yelling at you and fix it this way. So with double quotes, hopefully that's fixed now. OK, no, what'd I do wrong still? Yeah, exactly. I simply haven't declared bad. So fix 1 could be move it to the top of the file. But again, better practice is leave main at the top. And instead, what do I type at the very top of the file? Void bad, the same thing, but semicolon. All right, so now let's see if I fix this. Let me go back to the bottom. I'll zoom in at the bottom. Let me rerun make bad. OK, that's good. Bad. OK, so we're on our way. Not an interesting program. But now suppose you do this. Interesting thing here is that main is calling bad, but that's it. I could really create an interesting quandary here and perhaps send a message along the lines of don't do this if I did something like this. What if I did bad in here and I passed in first n gets n plus 1, or let me keep it simple, n plus plus, and pass in bad here. So what's going to happen? This should hopefully start messing with your mind. So main gets called. We initialize n to 0. We then pass that into bad. Now, quick sanity check. Is this a coincidence or necessary that I also called the input to bad n? So it's not necessary. This is actually just a coincidence. Why? This is actually maybe confusing. So I'll change it. Let me change it to I, and I'll change this to I, and I'll change this to I. Because again, I, or whatever I call it, is going to be a copy of n. But it doesn't matter if they're named the same, because they're in different scopes. So you can reuse names of variables if you want in this way. So OK, so main initializes n to 0, passes in 0 to bad. Bad takes as input that value 0, and it prints out 0. Then I gets incremented from 0 to 1. And then bad gets called with what input? 1. So what happens next? We don't go back to main yet. Instead, bad gets called again. So if you're kind of thinking through this linearly, we're chugging along here, 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 here. Then we do this again and call bad again. So at this point, bad takes as input 1, prints out 1, and then does what to I? Plus, plus. So it becomes 2. Then bad prints out 2, and then 3, and then 4. And why is this kind of a problem? All right, so it never stops, right? And you might have done this accidentally with infinite loops already, and that's kind of bad if you have an infinite loop that never stops because you messed up your condition. But now if you think about what's going on inside of the computer's memory, it's kind of worse when every time you call a function, it turns out it's using some amount of memory. In fact, it's using, let's say, a sliver's worth of RAM in your computer. But every time you call a function, it goes on top of the previous function that was called, on top, on top, on top. So even though bad is the same thing, every time you call it, you get a distinct sliver of memory again and again and again. And so if you kind of think through this, if you do this infinitely long, what's going to happen? Well, you're going to overflow your computer's RAM. And this is just the bottom of your RAM. If we actually redraw this and actually acknowledge that you only have a finite amount of memory, you've got a gigabyte or 2 gigabytes, you do not have an infinite amount of RAM, well, there's got to be something probably at the very top of that. And indeed there is. If you think again about your computer's memory as this big rectangle, the thing at the bottom now we'll call the stack. Every time you call a function, you just keep stacking more and more memory on top of the stack. But it turns out at the very top of your computer's memory, there's what's called the text segment. And text is just a fancy way of saying that's the zeros and ones that represent your actual compiled program. In order for them to run, when you double click them or type their command at the prompts, they get loaded into memory. So if nothing else, your own program is somewhere there in RAM. And if you keep calling bad, 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 what's going to happen? You're going to literally overwrite other stuff with the zeros and ones that represents bad's stack frame, its local variables. He only has one local variable, I, and that's 32 bits. So frankly, this is going to take a while to get all the way up to the very top if we're only doing it 32 bits at a time. But if we're doing it infinitely, we'll get there eventually. And you're going to start overwriting potentially important stuff. And this isn't quite how a bad guy would do it, but it's the same idea, whereby you can then change what code is inside of your own program and trick a program into executing something bad like disable the serial number prompt, or disable the password prompt, or give me administrator access. So I've compiled, let's recompile this now that I've introduced this infinite loop by way of calling bad, 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 and run this. And let's go ahead. Went a little long, but let's take our 2-minute break now, leave this up and running, and we'll come back and see if this is actually broken. Oh.